Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, formally, good evening grade 12s. As we can see here, this is probably something that really should scare you in a good way, is that we actually don't have a lot of time. Your finals start in 20 days. Okay, it's less than a month. Okay, it actually starts at the end of this month, 27th of October, and today is the 6th of October. You know, so the countdown is real. Okay, you finish your exams a little bit earlier. All right, in December. I think in our school we only started in November and we finished also quite late in December, but well before Christmas. But I mean, we finished at the beginning of December. So obviously we're not sure what, I'm not sure if you guys know. I don't know right now the dates of the exam for our subject, physical science. Okay, but we're going to do some revision tonight of term 3's work. Okay, so I'm going to pull up the 2019 November paper. I'm going to pull out the 2019 November paper. Okay. And we'll start with the November paper for physics. Just pull it up quickly. Where is it? Okay. For paper 1, we'll open this in a new tab. Okay. Now, my question that I'm going to ask the class currently is that paper 1 was the chosen topic for chosen paper rather for tonight's revision session. Okay, so before we get into the paper itself, let's just find out which topics would like to be revised. Okay, so we got a question to go through, a momentum question, which is question 4. All right, I'll just read the question, and it's 10 marks. It's very short, as it usually is. Okay, so a bullet moves east at a velocity of 480 meters per second, hits a wooden block, fixed floor. The bullet takes 0.01 seconds to move through the stationary block and emerges from the block at a velocity of 80 meters per second east. See the diagram below, and there's about 4.1 all the way to 4.2.2, so about basically 3 questions, all right, for you, all to the value of 10 marks. Okay, so that should take you 10 minutes. We'll mark this at 7 o'clock. So let's have a look here. We've read that the bullet passes through on the one side 480 meters per second. That's what it's flying at the block with, and exits the block at 80 meters per second. So obviously it loses about 400 meters per second inside the block. Okay. Explain what it is meant by isolated system as used in physics. All right. So I'll jump on and explain that so that nobody else has to go for that. It's fine. An isolated means, basically in layman's terms, let's just explain it in layman's terms so we can get everybody on the same page, and then we'll go for the physics. Okay, an isolated system means basically there's no outside interference from any other factor or force, you know, or system. All right, everything is isolated, it's taken out, it's on its own. Okay, but if you're going to use it as we've used it in physics, okay, if we explain 4.1 in this section, which is November 2019. Okay, if we have an isolated system in physics, it is a system on which either you can use the word resultant force or net external force. Resultant external or net external force is 0. Okay, it's all equal to 0. Or what you could say, An isolated system is one that has no net or no external force acting on it. In other words, there's no outside interference. All right? It is purely isolated. Now they say for 4.2, the magnitude of the momentum of the bullet before it enters the block is 24 kilograms per meters per second. Calculate the mass of the bullet. Well, we all know the momentum formula, right? P is equal to mass times velocity. P is the symbol for momentum. We were given P, so that is 24 is equal to the mass, which is unknown, but we know that the bullet was traveling at a speed of 480 meters per second. So if we divide both sides by 480, then therefore the mass of the bullet must be a whopping 0.5 kilograms. Okay. Which if we times by 1,000, just to get some accuracy, my mind is 50 grams. Okay, but remember in physics, so we measure everything in kilograms. And of course the last question there for 4.2.2 to end things off, give the net or the average net force exerted by the wooden block on the bullet. Okay, so this is how I'm going to go ahead and calculate it for 4.2.2. I'm going to say F net times delta T is equal to the change in momentum. Okay, now to narrow this down, F net times delta T must equal to, of course, the mass of the bullet, or the mass times velocity of the bullet initial minus the mass times velocity of the bullet, sorry, not initial, final minus MVI. So in other words, that's going to be 0.05 multiplied by 80, because that was the final velocity of the bullet, minus 0.05 multiplied by 480, which we all know is equal to actually 24. Okay, so it's up to you. Remember, we calculate the mass, so that over there times that must equal that. Okay, and we are trying to, let's see if I missed anything in the question. The bullet takes 0.01 seconds, okay, as it says there. So 0.01 seconds. So that's F net here multiplied by 0.01. Bracket there. Okay, so we need to take everything here, and so just put that all in our calculator. 0.05 multiplied by 80, that's 4, minus 24, which is minus 20, and let's divide that by 0.01, that's minus 2000. So F net is going to equal minus 2000 newtons, but that minus is just the direction, guys. So therefore we end off and we say F net is equal to 2000 newtons, and we add a direction and we say west. Okay, now there's a little section at the end of momentum called elastic and inelastic. Okay, before we get there, we must understand that this little law, okay, that's total linear momentum in an isolated system is constant, or is always conserved. Okay, which means total momentum before must equal total momentum after. Okay, now when we come to elastic versus inelastic collisions, let's just circle that for a moment. Okay, the definition is, again, as a bit of revision, because the last time we did this was in term 1, which was at the beginning of this year, and we're already at the end of the year already. Time is moving by so fast. A collision is considered, okay, if you don't know this or haven't forgotten this, write this down, is considered elastic if the total kinetic energy of the objects in the system during the collision is conserved or kept constant. Okay, in other words, EK initial, EKI, is equal to EKF. Not just EKI and EKF, but total, so sigma. Okay, I think it's the Greek symbol, sigma. Okay, total kinetic energy before is equal to total kinetic energy after. All right, which should make sense. Okay, the definition goes afterwards to say otherwise inelastic. Okay, so when we're looking at oh yes, question, yes, go for it.
The last equation EK, is that supposed to be sigma EK?
Yeah, I tried to draw it bigger
And then
so we can see it. Yeah.
and then the top equation, that's just sigma P initial.
Yeah, so that top equation there that's circled, before we get, so I just wanted everybody to understand, because I mean I was going to use sigma again down here, was that total momentum, the law of conservation of momentum, we mustn't forget that total linear momentum in an isolated system is constant, all right, which is total P, sigma Pi, total initial momentum must equal total final momentum.
Okay.
It's the same thing with mechanical energy. Emec at the top must equal Emec at the bottom if it's a roller coaster, or Emec at point A must equal Emec at point B. Basically showing conservation, that whatever's here must be equal there if it is conserved. If it's not conserved, then of course it'll be different. Right. So basically, in an elastic collision, total kinetic energy of the objects, not just of the object, but of the objects in the system, is the same. Okay. So, but remember, collisions are almost never elastic. Okay. Collisions between snooker balls, you know, if you play pool, if you play snooker, all right, are almost elastic. They are not 100% elastic. All right, they're almost elastic. Also, those bouncy balls that bounce very high have an almost elastic collision with the ground. All right, those the bouncy balls that you buy at like Crazy Store or something that all young people want because of the bounce that it makes. Okay, bounces extremely high. So basically, what would happen in an elastic collision, how that formula would look. All right, if you're just gonna isolate elastic here quickly. So we got obviously total EK initial must equal total EK final. So that'll be, of course, half M1 VI1 squared plus half mass of the second object times the initial velocity of the second object squared, all right, is equal to half the mass of the first object times that object's final velocity squared, plus half the second object's mass times the second object's final velocity, all squared. So this is that, all packed out. So it's the total kinetic energy of the objects before and after. Okay, if this is the case, that equal sign is very important, then we have an elastic collision. If this is not so, all right, if this is not so, in other words, if there is a line, in other words, saying that it's not equal, all right, then the above here, when it's not equal, would be a inelastic collision. Be an inelastic collision. All right. And the inelastic collision would be cars, all right, smashing into each other. Okay, meaning that the total kinetic energy before of the two objects does not equal that of the second, which would make sense because the velocities would obviously decrease. Okay. A little point of revision as well, maybe also in the subject of mechanics from grade 11, was we get two frictional formulas. Okay, we get the static frictional formula, which is the coefficient of static friction multiplied by the normal force, and then we get, of course, the kinetic Fk, which is mu k times the normal force as well. Now, we mustn't get confused with the normal force. Okay, remember the normal force is opposite or equal to W, which is equal to mass times gravity. So often in a question, okay, we'll be given the normal force, but we don't know how to calculate the normal force. It's the same value as mass times gravity. Same value, okay? Because the normal force pushes up while gravity pushes down. That's why they cancel each other out, okay? And that's why we stay on the ground, okay, more or less, and we don't fall through it, right? Otherwise, we'd all be chilling at the center of the earth. Okay, smelling like crispy bacon or crispy whatever you want to call it. So the coefficient is usually given, okay, and if you're trying to calculate the force of friction, either static or kinetic. Static means obviously when the object is standing still. Kinetic obviously means when the object is moving. So if the object is moving, of course, you've got kinetic friction. Okay, if the object is standing still, all right, there's static friction. Okay. But the coefficient, if I could just explain what the coefficient is quickly. I'll just explain that coefficient part again, okay? The coefficient will either have to be obviously worked out, and you can work out it by if you obviously get the value of friction, if that is given, you can calculate the coefficient. But the coefficient of kinetic, which is mu k in the formula, that little funny Greekish looking u, which is called mu, and mu s there in the static friction formula, that there is there for basically that depends on the nature of the surface. Okay, so nothing that you do to the mass, the type of object, changing the speed, putting the object maybe on a maybe let's not say that, but I mean changing the speed of the kinetic energy, whatever you do, that's not going to change the coefficient of the of static or kinetic friction. The coefficient is only dependent on the nature of the surface. So the coefficient of kinetic friction or static friction will differ if the object is on a wooden table versus a granite table. That's the only thing that's going to change that coefficient, right? Is the nature of the surface. If the nature of the surface doesn't change, but the object changes, coefficient will change, will stay the same. Normal force will be different and all those things, but coefficient will stay the same because of the nature of the surface. Grade 12. So I'd like to take the liberty of going through the final paper 1 topic that we have not exactly gone through much. Last week, or 2 weeks ago rather, last week we took off. Last week we, or 2 weeks ago again, sorry, we did grade 11 revision on electric circuits, just on electric circuits. What we're going to do now is we're going to actually have a look at some grade 12 one. This is a typical grade 12 circuit. Very nice question. In the circuit diagram below, resistor R with a resistance of 5.6 ohms is connected together with a switch. A ammeter with a high resistance voltmeter connected to a battery with an unknown internal resistance of R. Now in grade 12, we bring into consideration, or into the picture, we bring external or internal resistance. We're used to external resistance, but now we've actually learned that a battery itself has internal resistance, okay, which also would resist, of course, the outlet of its voltage. We can ignore the resistance of the wires, they're quite negligible, and they give us a graph. Okay, now they say the graph shows the potential difference across the terminals of the battery as a function of time. So we got voltage, potential difference 13, then over time we see the voltage drop to 10.5. Okay, first question, is define EMF of a battery. Oh, sorry guys, hold on, something just bugged out here on my screen. Define EMF of the battery. Now, EMF of a battery, what we can define as layman's terms, would obviously be the potential difference, all right, of the battery. Okay, but in actual physics, it is the maximum energy provided, which is the same as work done by a battery per coulomb. Okay, am I spelling coulomb right? Yes, per coulomb or unit charge passing through it. Okay, that is EMF of a battery. Okay, if you don't know this definition, please take it down. It will most likely come up. Okay, most likely or highly likely. All right. Write down the value of the EMF of the battery. Now, the EMF of the battery obviously is the potential difference that the battery comes in the package with. Okay, what it can give, what it can let out. Okay, so potential difference, of course, or potential difference or EMF of the battery would definitely be 13. It's the highest point there of the graph. Okay, when the voltage drops, it obviously means that some voltage has been released. All right. So definitely at what it starts at before the switch gets closed. Obviously there's some lost volts there, but here 13 is the EMF of the battery, so 13 volts. 8.3.1 looks like it's going to be some calculation questions. When switch S is closed, calculate the resistance current through resistor R. Now if we go look here, we've got resistor R that has a value of 5.6 ohms, and they want the current. That's grade 11 work. Okay. So we again use R is equal to V over I. We go straight there. 5.6 is equal to 10.5 or 10.5. Why do we use 10.5? Okay, because switch S is now closed. They say switch S is closed. They basically screamed it at your face. That's why they typed it in capital letters. It's closed. So now when switch is closed, obviously voltage has now dropped because some is lost, of course. So voltage is now dropped. So that means this must be the voltage in the circuit now. 10.5. Okay, divided by I, which is unknown. Okay, so we're going to have I is going to equal to V over R. So that's 10.5 divided by 5.6. And therefore, your current in the circuit is going to equal 1.88 amps. Write amps a little clearer there. Okay, well, everybody should understand exactly what I just did. Okay, cool. If there are any questions, please don't hesitate to ask. Okay, let's see if I have some space at the bottom here that I can possibly still. No, I think I've got enough here. 8.3.2. 8.3.2 says calculate the power dissipated in the resistor. Okay, now we're bringing in a power formula. Okay, now we've got three options for power. Okay, now power, also something that we haven't exactly looked at yet in great detail. All right, but we will. But let's just introduce it now through this little question. Okay, power. All right, basically the work done by an object in a given time. Okay, W divided by T. Okay, but we've got different formulae also for W. Okay, so power can equal either P is equal to V times I, or equal to I squared times R. Okay, or it can equal to V squared over R. Any one of those three. Okay, you can use. Now, dependent on which one you're going to use, you're going to get a different answer. Okay, for some strange reason. Let's go ahead with this one. Okay, so that's going to equal the voltage, which was 10.5 multiply by 1,88, and that's going to equal 19,74 watts. Power is always measured in watts. All right, I think power was discussed last year in grade 11. Actually, I can actually confirm that in my grade 11 textbook, actually, where power, I think, is discussed. Maybe not in the greatest of detail, but it is discussed. Yes, okay, let's just go back here quickly. Is mentioned, I think it is, electric circuits. Let's see, yes, it is, power is mentioned, it is. So power was taught last year, okay? So this is basically a grade 11 question again, I mean, with the simplicity of it as well, okay? Depending on which one you used, okay? Now 8.3.3 is the internal resistance question, okay? Calculate the internal resistance of the battery, okay? Now there is a formula that is given, okay, that says that the EMF is equal to the current in the circuit times the external resistance plus the internal resistance, and that should give you what the total EMF is equal to, okay? Now if we multiply in here quickly, we'll have I times capital R plus I times little r. Now what is equal to I times R? Voltage, correct? Voltage is equal to I times R. That's simple, right? Or simple enough. I times R, because that is external resistance, is equal to external voltage, Vxt or Ext. Current times the internal resistance must be the internal voltage. So these two things stands for these two things, okay, and vice versa, okay, even though they will have different values, okay. Now V external will mean, okay, V external is going to be everything in the outside of the circuit when the switch is closed. So what's the voltmeter reading when the switch is closed? From the graph we saw it was 10.5. EMF was equal to 13 plus V internal. All right, plus V internal. So V internal must be 13 minus 10.5. So V internal must equal 2.5 volts. All right, and that's how much was obviously lost in the circuit. Okay, so what do? We can say, well, V internal, the formula, obviously equals that, I times little r. So now that we know what it is, 2.5 is equal to, the current was 1,88. We have little r there. 2.5 divided by 1,88. Therefore, R will equal to 1,31 ohms. You didn't have to even acknowledge this. All you could have done is also just sub that into the formula here, and we still would have gotten the same answer, to be honest. Right? We still would have gotten the same answer, but I needed to stipulate what I times big R is and what I times little r is. 8.4 says, now two identical resistors, each with resistance X, are connected in the same circuit with switch S closed as shown below. So you should recognize it's the same circuit basically over here. So, let's just go up here quickly. The same circuit, we just connected the two series or two resistors in series over here in parallel with the 5.6. So it's the same circuit. Okay, the ammeter reading now increases to 4 amps. The ammeter reading was 1,88 first. Now it is 4 amps. Okay, it increases. How would the voltmeter reading change? Okay, now they're trying to get theoretical with you guys. How will the voltmeter reading change? Okay, would it increase, decrease, or remain the same? Give a reason for your answer by referring to V internal. Now, V internal is the same as the current times the internal resistance. Okay. I times little r. So I is obviously increased, so V internal increases. So V internal increases. That means we're going to have a smaller V external. from our EMF, alright? Because your EMF minus your V internal will give you your V external, or the voltage in the rest of the circuit, outside of the battery, okay? So if that is the case, then for 8.4.1, the answer is decreases, and referring to our answer, right, we will say that V internal, all right, increases. The internal voltage increases. Okay. Now, the second question, which I'm going to need a new page for, unfortunately, says calculate resistance X. Okay. Now this one is really not, it's not easy, guys. Right? It's really not easy. Okay. What needs to happen is I'm going to pick, I think I've got a pretty good method on how to calculate this. There's more than one way. I think there's more than 2 or 3 ways on how to calculate this. But let's use what we just taught earlier. Let's use the EMF is equal to I times capital R plus little r. Okay, so the EMF was equal to 13. Okay. And that was equal to the current, they say increases to 4. Okay. And we got R there, which is the same as R external. Okay. Plus 1,31, which was the internal resistance that we just calculated earlier. Okay. So if we got 13 is going to equal to 4R plus, what's 1,31 times 4? 1,31 times 4. That's equal to plus 5,24. So 13 minus that answer, and let's divide that by 4. We're basically going to get external resistance in the circuit is going to equal to 1,94 ohms. Okay. That's the value of the external resistance, which is the same as the total resistance in the circuit. Now, therefore, we have our R parallel formula. RP, okay, is equal to R1, R2 plus R1 plus R2. Now, we must understand that these two resistors in series with each other, X and X, are both in parallel to resistor R. So these two count as one if resistor R had a pair of eyes and had to look at both of them. They count as one because they are in one branch. They are not separated into another 2 branches. They are in line, in series with each other, so they count as one to resistor R. So we can count X and X as R2 here. So basically R1, 1,94, which is the total resistance in the circuit, which would be the parallel, is equal to 5,6 times R2 over 5,6 plus R2, which is both X and X. Okay. Now, how do we do this? Okay. This is going to be another big question. Okay, we've got to get rid of the numerator, so we're going to have 1,9 denominator, sorry, times 5,6 plus R2 is going to equal 5,6 R2. So 1,94 times 5,6. That's going to be, I'm going to need to go to the top of this page again. And let me just rule a line off. That's going to be 10,864. I'll write the entire number down. All right. Let me just see here. Yeah. Times that. All right. Plus 1,94 R2. That's going to equal 5,6 R2. Okay. So we can take that over. So we'll have 10,864 is equal to 5,6 minus 1.94. I messed up that question, sorry. 1.94. 3,66. R2. Divide both sides by 3,66. 3,864 divided by answer. Divide both sides by 3,66, sorry. And therefore the second resistor, R2, which will be X and X together, will be 2,968, which will be 2,97 ohms. Now, we must remember there are two identical resistors with the same value, X and X. That's why they got the same variable. So, the value of X, all right, is going to equal half of 2,97 ohms. All right? And if we do that, divide that by 2, therefore, X is going to equal 1,49 ohms. 1,49 ohms. So each resistor, as they said in the question, two identical resistors, X and X, are both 1,49 ohms each. So thank you, grade 12s, for joining me tonight on this little revision session that we've had from term 3. Thanks for all the questions that were asked. Proud of you guys for the results that you achieved, and anybody watching this video that got some good results and is happy with the results from their mock exams, congratulations. If you are not so proud, don't worry about it. We can turn it around in term 4 at our finals. We can turn it around. So let's stay optimistic, and let's work hard. Okay, hope you enjoyed this little tutorial video, and we will catch you in the next one. Please don't forget to like and comment on the video, as well as subscribe to our channel, Good Better Best Online Videos.